The universe stretches out in all directions, a seemingly infinite expanse filled with wonders that defy comprehension. And yet, what lies beyond the edges of our own galaxy? The Milky Way holds secrets that could rewrite everything we think we know about reality. Distant galaxies, trillions of light years away, are not just faint specks of light in the night sky. They are cosmic time capsules, preserving stories of the universe's birth, growth, and ultimate fate. In this video, we'll dive into 25 mind-bending discoveries about these far-off galaxies, each more astonishing than the last. From galaxies that defy the laws of physics to black holes so enormous they warp the fabric of space-time, these findings challenge our understanding of the cosmos and our place within it. Why does studying these galaxies matter? Because they hold the key to unraveling the deepest mysteries of existence. What if everything we've discovered so far is just the tip of the iceberg? Get ready to embark on a journey that will leave you in awe, questioning the very nature of reality itself. Imagine staring at what appears to be a blank, empty patch of sky, a void so unremarkable it might seem like nothingness itself. Then, with the power of the Hubble Space Telescope, that same patch transforms into a stunning tapestry of light, revealing thousands of galaxies swirling in the cosmic depths. This is the story of the Hubble Deep Field, one of the most profound images ever captured in the history of astronomy. In 1995, astronomers pointed Hubble at a tiny, seemingly barren region of space, a spot no larger than a grain of sand held at arm's length. What they found was astonishing, a breathtaking collection of galaxies, each one a universe unto itself, brimming with stars, planets, and untold mysteries. This single image shattered our understanding of the universe's scale. Before the Hubble Deep Field, we had only glimpsed the universe's grandeur. But now we were confronted with a reality far more vast and complex than anyone had imagined. The sheer number of galaxies in that tiny patch suggested an almost incomprehensible truth: the universe is not just large. It is teeming with countless galaxies, each a beacon of light from billions of years ago. What does this mean for our understanding of the cosmos? For one, it forces us to confront the sheer enormity of the universe. If such a small fraction of the sky holds thousands of galaxies, how many more are out there waiting to be discovered? Experts estimate that the observable universe could contain upwards of 2 trillion galaxies, a number so staggering it defies human comprehension. The Hubble Deep Field also gave us a glimpse into the universe's evolution. By studying these distant galaxies, astronomers can trace the history of the cosmos from its earliest days to its current state, piecing together the story of how everything we know came to be. This groundbreaking discovery didn't just reshape our understanding of the universe, it ignited a new era of exploration. It paved the way for even more ambitious projects like the James Webb Space Telescope, which now peers even deeper into the cosmos. The Hubble Deep Field reminds us that even in the emptiest corners of space, there is a universe brimming with wonders waiting to be uncovered. And with every new discovery, we inch closer to answering the ultimate question: just how vast and mysterious is the cosmos? As we peer deeper into the cosmos, we uncover galaxies so ancient they seem to defy the very timeline of the universe itself. Astronomers have stumbled upon a paradox that has left even the most seasoned experts scratching their heads. Galaxies that appear older than the universe's estimated age of about 13.8 billion years. How can this be? If the universe began with the Big Bang, how did these galaxies form so quickly? This discovery doesn't just raise eyebrows, it throws a wrench into our understanding of cosmic history. One of the most baffling examples is GNZ 11, a galaxy observed by the Hubble Space Telescope. GNZ 11 is so distant that its light has traveled for over 13.4 billion years to reach us, meaning we're seeing it as it was just 400 million years after the Big Bang. But here's the catch: the galaxy is already mature, filled with stars that must have formed much earlier than current models predict. As astronomer Garth Illingworth once put it, "We're seeing galaxies in their infancy, yet they're already far more developed than we thought possible." This challenges the very foundation of the Big Bang theory, which suggests that the universe needed time to cool and expand before galaxies could form. So, how do we reconcile this paradox? One leading theory is that the early universe was far more dynamic and accelerated than we imagined. Perhaps some regions of space experienced rapid growth, allowing galaxies to form much sooner than expected. Another possibility is that our current methods for estimating the universe's age are incomplete or flawed. Could dark energy, the mysterious force driving the universe's expansion, play a role in this discrepancy? Some scientists even speculate that the universe might be older than we think, with the Big Bang marking a major event rather than the absolute beginning of everything. This mystery doesn't just shake up our understanding of galaxies, it forces us to rethink the very nature of time and space. If galaxies can form faster than our models predict, what else might we be missing? Could there be other cosmic phenomena that operate on timelines we can't yet comprehend? Astronomers continue to grapple with these questions, using cutting-edge tools like the James Webb Space Telescope to probe deeper into the universe's past. As we uncover more about these ancient galaxies, one thing becomes clear: the universe is far more complex and enigmatic than we ever imagined. Each discovery peels back another layer of the cosmic onion, revealing questions that challenge our most fundamental theories. And while it's tempting to seek definitive answers, perhaps the true beauty lies in the mystery itself, a reminder that the universe still holds countless secrets waiting to be unlocked. In the vast expanse of the cosmos, there's an invisible force at work, one that shapes galaxies, bends light, and governs the very structure of the universe. Yet, despite its profound influence, we've never seen it directly. This enigmatic force is dark matter, and it's one of the greatest mysteries in modern science. For decades, astronomers have known that something unseen is pulling the strings, dictating how galaxies rotate, cluster, and evolve. But what is dark matter, and why does it remain so elusive? The first clues to its existence came from something unexpected: the way galaxies spin. In the 1970s, astronomer Vera Rubin noticed that stars on the outer edges of galaxies were moving far too quickly to be explained by the visible matter alone. According to the laws of physics, these stars should be flung into space, yet they remain in orbit. The only explanation: a massive, invisible halo of dark matter surrounding the galaxy, holding everything together with its gravitational pull. This discovery revolutionized our understanding of the cosmos, revealing that what we see, stars, gas, and dust, is just a fraction of what's really out there. But dark matter's fingerprints don't stop there. Another key piece of evidence comes from gravitational lensing, a phenomenon where the immense gravity of a massive object, like a galaxy cluster, bends the light from objects behind it. Sometimes the distortion is far greater than the visible mass can account for, suggesting that dark matter is amplifying the effect. These cosmic magnifying glasses allow us to map the invisible scaffolding of the universe, showing how dark matter weaves a vast, intricate web that connects galaxies across billions of light years. Despite its pervasive presence, dark matter has never been directly detected. Scientists have built underground detectors, launched satellites, and conducted countless experiments, all in search of this mysterious substance. Some theories suggest it could be made of particles that interact only weakly with ordinary matter, while others propose it might be part of a new, undiscovered branch of physics. Whatever it is, its influence on distant galaxies is undeniable. Without dark matter, galaxies wouldn't have the gravitational glue needed to form and evolve into the complex structures we observe today. So, what if dark matter holds the key to understanding the universe? Its role in shaping galaxies is just the beginning. Some researchers believe that dark matter could explain why the universe is expanding at an accelerating rate, or even provide clues about the nature of dark energy, another cosmic enigma. Others think it might help us unlock the secrets of the early universe, revealing how the first galaxies emerged from the primordial soup of the Big Bang. As we continue to probe the cosmos, the search for dark matter remains one of the most exciting frontiers in science. It's a reminder that the universe is far stranger and more complex than we can imagine, filled with mysteries that challenge our understanding of reality. And while we may not yet know what dark matter is, one thing is certain: its invisible hand has shaped the universe in ways we're only just beginning to comprehend. At the heart of every galaxy, there's a cosmic behemoth lurking in the shadows, a supermassive black hole. These gravitational giants, millions or even billions of times the mass of our Sun, are more than just passive observers in the galactic drama. They are active players shaping the destiny of the galaxies they inhabit. One of the most startling discoveries in modern astronomy is that supermassive black holes aren't rare anomalies. They're a universal feature found at the center of almost every galaxy we've observed. But how do these colossal entities form, and what role do they play in the life of a galaxy? Supermassive black holes are like invisible puppeteers pulling the strings of galactic evolution. Their immense gravity affects everything around them, from the orbits of stars to the flow of gas and dust. In some cases, this influence can be destructive. When matter falls into a black hole, it heats up and emits intense radiation, creating what's known as an active galactic nucleus. This process can trigger powerful jets of energy that shoot out into space, heating up nearby gas and preventing it from cooling and forming new stars. In this way, supermassive black holes can stifle star formation, effectively putting the brakes on a galaxy's growth, but their role isn't purely destructive. In other cases, the energy released by supermassive black holes can actually spark star formation. As jets and winds from the black hole collide with surrounding gas, they can compress it, triggering the birth of new stars. This delicate balance between creation and destruction is a key factor in how galaxies evolve over billions of years. Recent discoveries have shed new light on these enigmatic objects. For instance, astronomers have found that supermassive black holes are often linked to quasars, the brightest objects in the universe. Quasars occur when a black hole is actively feeding on massive amounts of matter, releasing energy that outshines entire galaxies. By studying quasars, scientists can trace the growth of black holes and their impact on the cosmos. Yet, one of the biggest mysteries remains: how did these supermassive black holes grow so large so quickly? Some of the oldest quasars we've observed existed when the universe was less than 1 billion years old, raising questions about how such massive objects could form in such a short time. One theory suggests that supermassive black holes might have grown from smaller, seed black holes, formed from the collapse of the universe's first stars. Others propose that they could have formed directly from the collapse of massive gas clouds in the early universe. The study of supermassive black holes is more than an exercise in cosmic curiosity. It's a window into understanding the forces that shape the universe we see today. From their influence on star formation to their role in powering quasars, these gravitational giants are central to the story of galactic evolution. And as we continue to explore the cosmos, each discovery brings us closer to unraveling the secrets of these enigmatic objects and the universe they help shape. Galaxies, for all their beauty and majesty, are not solitary actors in the cosmic theater. They exist in a dynamic, ever-changing environment where gravitational forces draw them into a celestial dance, one that can sometimes turn violent. This brings us to the phenomenon of galactic cannibalism, a process where larger galaxies devour smaller ones, reshaping the structure of the universe over billions of years. It's a story of cosmic competition where survival hinges on strength and size. Picture this: two galaxies bound by gravity, slowly spiraling toward each other. Over millions of years, their orbits tighten until they finally collide. But this isn't a catastrophic explosion. It's more like a gradual merging, a cosmic tug of war where the larger galaxy eventually absorbs the smaller one. The result, a new, larger galaxy with a dramatically altered structure. This process is known as galactic cannibalism, and it's a key driver of galactic evolution. One of the most famous examples is the Milky Way's own history. Our galaxy, as it turns out, has a past filled with mergers. Astronomers have discovered remnants of smaller galaxies that were absorbed by the Milky Way, their stars now scattered across its halo. One such example is the Gaia-Enceladus galaxy, which collided with the Milky Way around 10 billion years ago. This ancient merger not only increased the Milky Way's size, but also influenced its structure and star formation. But galactic cannibalism isn't just about size, it's about transformation. When galaxies merge, the gravitational forces involved can trigger bursts of star formation as gas and dust are compressed and heated. This can lead to the creation of millions of new stars in a relatively short period. At the same time, these collisions can distort the shapes of the galaxies involved, turning spirals into ellipticals or creating entirely new structures. Take the Antennae galaxies, for instance. Located about 45 million light-years away, this pair of colliding galaxies is a textbook example of galactic cannibalism in action. The gravitational interaction has pulled long streams of stars and gas from each galaxy, creating the antennae that give them their name. Within these streams, astronomers have observed intense star formation, with massive star clusters forming at an astonishing rate. It's a vivid reminder of the dramatic effects these cosmic collisions can have. So, why does this matter? Galactic cannibalism isn't just a fascinating phenomenon. It's a crucial part of the cosmic life cycle. Through these mergers, galaxies grow, evolve, and transform, shaping the universe as we know it. They're also a reminder of the interconnected nature of the cosmos, where even the largest structures are influenced by their interactions with others. As we continue to study these events, each discovery adds a new piece to the puzzle of galactic evolution. From the Milky Way's past to the Antennae galaxies present, these cosmic collisions reveal a universe in constant motion, where change is the only constant. And while the process may seem violent, it's also a testament to the universe's ability to create, adapt, and thrive. In the vast cosmic web, galaxies aren't just drifting aimlessly, they're being drawn towards something immense, something hidden. This mysterious force is known as the Great Attractor, a gravitational anomaly so powerful it's pulling thousands of galaxies, including our own Milky Way, toward it at incredible speeds. Located about 220 million light-years away in the direction of the constellation Centaurus, the Great Attractor has become one of the most intriguing puzzles in modern astronomy. But what exactly is it, and why does it hold such a powerful sway over the motion of galaxies? The story of the Great Attractor began in the 1970s, when astronomers noticed something unusual. Galaxies in our local region of the universe all seemed to be moving in the same direction, as if being pulled by an unseen hand. This motion couldn't be explained by the distribution of visible matter alone, leading scientists to theorize the existence of a massive concentration of mass, something far greater than any known galaxy or cluster. The Great Attractor was born not as a visible object, but as a gravitational enigma hidden behind the plane of the Milky Way, obscured by dust and stars. What makes this phenomenon even more fascinating is its relationship with dark energy, the mysterious force driving the universe's accelerated expansion. While the Great Attractor's immense gravity tugs galaxies toward it, dark energy works in the opposite direction, pushing the cosmos apart. This cosmic tug of war raises profound questions about the balance of forces in the universe. How can such a massive gravitational force exist in a universe dominated by dark energy? And what does it tell us about the distribution of matter on the largest scales? Despite its elusive nature, astronomers have made strides in mapping the Great Attractor's influence. Using tools like the X-ray Observatory Chandra and the infrared telescope WISE, they've peered through the Milky Way's dust to reveal clusters of galaxies in the region, hinting at the source of the gravitational pull. One of the most significant discoveries is the Norma cluster, a dense grouping of galaxies that may be part of the Great Attractor's core. Yet, even with these findings, the true nature of this cosmic giant remains shrouded in mystery. This raises a tantalizing question. What lies beyond the Great Attractor? Some scientists believe it might be part of an even larger structure, connected to other superclusters in a vast cosmic network known as the Laniakea supercluster. This would suggest that the Great Attractor isn't just a local anomaly but a piece of a much larger puzzle, one that could redefine our understanding of the universe's structure. The Great Attractor is more than just a scientific curiosity. It's a reminder of how much we still have to learn about the cosmos. It challenges us to look beyond the visible, to question our assumptions, and to explore the hidden forces shaping the universe. As we continue to study this gravitational giant, each discovery brings us closer to understanding its secrets and perhaps the true nature of the cosmos itself. In a universe dominated by the invisible grip of dark matter, the discovery of galaxies seemingly devoid of this mysterious substance has sent shockwaves through the scientific community. These galaxies, like NGC 1052 DF2, stand as cosmic outliers, defying one of the most fundamental principles of modern astrophysics. If dark matter is the glue that holds galaxies together, how can these galaxies exist without it? This discovery isn't just a curiosity, it's a riddle that challenges our understanding of how galaxies form and evolve. The story began in 2018 when astronomers observed that NGC 1052 DF2, a faint, diffuse galaxy, didn't behave as expected. Stars within it were moving far slower than predicted, suggesting the galaxy lacked the gravitational pull of dark matter. This was unprecedented. Up until then, every galaxy studied had shown signs of dark matter's influence, either through its gravitational effects on stars or its role in bending light. The absence of dark matter in NGC 1052 DF2 raised a profound question. Are these galaxies rare anomalies, or do they hint at a deeper, more complex reality? One leading theory suggests that these galaxies might have formed differently than most. Instead of emerging from the gravitational pull of dark matter, they could have been born from the tidal forces of a larger galaxy, stripping away their dark matter in the process. Another possibility is that dark matter was somehow expelled from these galaxies, though how and why remains unclear. Whatever the explanation, these discoveries force us to reconsider the role of dark matter in galactic formation. Is it always essential, or are there alternative pathways for galaxies to take shape? Experts are divided on what these galaxies mean for our understanding of the universe. Some argue they're simply outliers, rare exceptions in a cosmos where dark matter reigns supreme. Others believe they could be evidence of a broader mystery, a hint that dark matter behaves in ways we don't yet understand. As astrophysicist Pieter van Dokkum puts it, finding galaxies without dark matter is like finding a car without an engine. It forces us to rethink how galaxies work. To solve this cosmic puzzle, astronomers are turning to advanced tools like the James Webb Space Telescope and next-generation observatories. These instruments allow us to peer deeper into the universe's history, searching for more galaxies that lack dark matter and studying their properties in detail. By mapping their distribution and evolution, scientists hope to uncover whether these galaxies are truly unique or part of a larger, yet to be understood phenomenon. The discovery of galaxies without dark matter reminds us that the universe is full of surprises. It challenges us to question our assumptions, explore new possibilities, and embrace the unknown. Whether these galaxies are anomalies or clues to a deeper mystery, they underscore the complexity of the cosmos and the endless potential for discovery. As we continue to probe their secrets, one thing is certain: the universe is far stranger and more wondrous than we ever imagined. Tucked away in the depths of space lies a structure so vast it defies imagination: the Hercules-Corona Borealis Great Wall. Discovered in 2013, this immense collection of galaxies stretches over an astonishing 10 billion light-years, making it the largest known structure in the universe. To put that into perspective, it's so enormous that it would take light, the fastest thing in existence, 10 billion years to travel from one end to the other. This isn't just a record-breaking cosmic feature, it's a discovery that challenges one of the foundational principles of cosmology. The cosmological principle, a cornerstone of modern astronomy, states that on the largest scales, the universe is uniform and homogeneous. In simpler terms, it suggests that no matter where you look, the cosmos should appear roughly the same. But the Hercules-Corona Borealis Great Wall throws a wrench into this idea. Its sheer size and density of galaxies stand in stark contrast to the principle's expectation of uniformity. As cosmologist Istvan Horvath, one of the discoverers, remarked, this structure challenges our understanding of the universe's large-scale structure. It's like finding a mountain range in a place where we expected a flat plain. So, how did this colossal structure form? One theory points to the early universe, where fluctuations in density could have seeded the growth of such massive formations. Another possibility is that it's the result of cosmic filaments, thread-like structures of dark matter drawing galaxies together into these vast webs. Whatever the cause, the Hercules-Corona Borealis Great Wall forces us to reconsider what we thought we knew about the universe's architecture. The implications of this discovery are profound. If structures of this scale exist, what does that mean for our understanding of the universe's limits? Could there be even larger formations waiting to be discovered? And how does this fit into our models of cosmic evolution? These questions aren't just academic. They push the boundaries of our knowledge and challenge us to rethink the very framework of cosmology. But perhaps the most exciting aspect of the Hercules-Corona Borealis Great Wall is what it represents, a reminder that the universe is far more complex and mysterious than we can imagine. Just when we think we've mapped its edges or understood its rules, it reveals something new and extraordinary. This discovery isn't just about breaking records, it's about expanding our horizons and embracing the endless possibilities of exploration. As we continue to study this immense structure and others like it, each finding brings us closer to understanding the universe's true nature. The Hercules-Corona Borealis Great Wall isn't just a cosmic marvel, it's a beacon, guiding us toward new questions, new discoveries, and a deeper appreciation of the cosmos's boundless wonders. Journey beyond the familiar spiral and elliptical galaxies, and you'll encounter a cosmic rarity that seems almost too strange to be real: galaxies with two nuclei. These unusual structures, where two bright, dense centers reside within a single galaxy, challenge our assumptions about galactic formation and evolution. How can a galaxy have two hearts? The answer lies in the violent, dynamic processes that shape the universe. One of the most plausible explanations for these double nuclei galaxies is the aftermath of galactic mergers. When two galaxies collide, their supermassive black holes, often hidden at their cores, are drawn together by gravity. Over time, these black holes may begin to orbit each other, creating a binary system that appears as a double nucleus. However, this process isn't instantaneous. It can take millions or even billions of years for the black holes to merge, during which time they continue to influence their surroundings, shaping the galaxy's structure and behavior. Another theory suggests that some double nuclei galaxies might not involve mergers at all. Instead, they could be the result of a single supermassive black hole that's actively feeding on surrounding material. As gas and dust spiral into the black hole, they form an accretion disk that can sometimes appear as a second nucleus due to its brightness. This phenomenon, while rarer, offers a fascinating glimpse into the complex interactions between black holes and their host galaxies. Observations of double nuclei galaxies have provided valuable insights into these processes. Take, for example, the galaxy Markarian 799, which features two distinct nuclei separated by about 800 light-years. Studies suggest that these nuclei are the result of a recent merger, with the two supermassive black holes still in the process of spiraling toward each other. Similarly, simulations have shown that such mergers can trigger bursts of star formation and alter the galaxy's shape, leaving behind a unique cosmic fingerprint. So, what do these galaxies tell us about the universe? For one, they highlight the importance of interactions in shaping galactic evolution. They also provide a unique laboratory for studying the behavior of supermassive black holes, particularly how they merge and influence their surroundings. As astrophysicist Tamara Bogdanovic puts it, double nuclei galaxies are like cosmic experiments, offering us a front-row seat to some of the most dramatic events in the universe. But the story doesn't end there. These galaxies also raise intriguing questions about the future of the cosmos. When supermassive black holes eventually merge, they release gravitational waves, ripples in space-time that can be detected by observatories like LIGO and Virgo. By studying double nuclei galaxies, we're not just uncovering their secrets, we're also preparing to witness the next chapter in the universe's grand narrative. Galaxies with double nuclei remind us that the universe is a place of endless variety and surprise. They challenge us to rethink our assumptions and explore the complex, often chaotic processes that drive cosmic evolution. And as we continue to study these celestial oddities, each discovery brings us closer to understanding the intricate dance of galaxies, black holes, and the forces that shape them. Imagine a galaxy as vast as the Milky Way, stretching across hundreds of thousands of light-years, but with so few stars that it appears almost ghostly against the backdrop of space. These are ultra-diffuse galaxies, ethereal cosmic structures that defy our expectations of what a galaxy should look like. While they are as large as our own Milky Way, their sparse stellar populations make them incredibly faint, often blending into the darkness of the universe. But don't let their ghostly appearance fool you. These galaxies are packed with mysteries that are reshaping our understanding of star formation, dark matter, and galactic evolution. Ultra-diffuse galaxies were first discovered in large numbers in the Coma cluster in 2015, though their faintness had made them easy to overlook in earlier surveys. Unlike the bright, densely packed stars of typical galaxies, these objects contain only about 1% of the stars found in a galaxy like the Milky Way. This raises an immediate question: how can a galaxy so large have so few stars? The answer lies in their unique formation and environment. Some theories suggest they may have formed in regions where star formation was naturally suppressed, perhaps due to a lack of gas or intense radiation from nearby galaxies. Others propose that these galaxies might be the remnants of larger galaxies that were stripped of their stars and gassed through gravitational interactions. One of the most intriguing aspects of ultra-diffuse galaxies is their relationship with dark matter. In some cases, these galaxies appear to have a normal amount of dark matter, holding them together despite their sparse stellar populations. In others, they seem to have very little dark matter at all, which is highly unusual for galaxies of their size. This inconsistency has sparked a heated debate among astronomers. Are these galaxies missing dark matter, or are we simply unable to detect it? Could they be unique products of galactic evolution, or do they represent a completely different class of objects altogether? The study of ultra-diffuse galaxies offers a unique window into the processes that shape galaxies. Their faintness makes them challenging to observe, but advanced telescopes like the Hubble Space Telescope and the James Webb Space Telescope are now shedding light on their secrets. By studying their structure, composition, and distribution, astronomers hope to uncover clues about the conditions that allowed these ghostly galaxies to form and survive in the harsh environment of the cosmos. These enigmatic objects remind us that the universe is full of surprises. They challenge our assumptions, push the boundaries of our knowledge, and inspire us to ask new questions. Whether they're remnants of cosmic collisions, outliers of galactic evolution, or something entirely unexpected, ultra-diffuse galaxies are a testament to the complexity and diversity of the universe. And as we continue to explore their mysteries, each discovery brings us closer to understanding the forces that shape the cosmos and our place within it. Nestled in the far reaches of the cosmos lies a beacon of light so ancient it predates nearly everything we know, the galaxy GNZ 11. Discovered in 2016, this celestial time capsule holds the title of the farthest galaxy ever observed, a staggering 13.4 billion light-years away. To put it simply, we're seeing it as it was just 400 million years after the Big Bang, a time when the universe was in its infancy. GNZ 11 isn't just a record breaker, it's a window into a primordial era, offering clues about how the first galaxies and stars came to be. What makes GNZ 11 so extraordinary isn't just its distance but its maturity. Despite its early place in cosmic history, this galaxy is surprisingly well developed, filled with stars that must have formed much earlier than current models predict. This raises an intriguing question. How did galaxies like GNZ 11 grow so quickly in the universe's formative years? Some scientists suggest that the early universe was a more dynamic and accelerated place than we imagined, with regions of space experiencing rapid star formation. Others speculate that GNZ 11 might have been born from the collapse of massive gas clouds, bypassing the gradual buildup of smaller structures. Studying galaxies like GNZ 11 is no small feat. Observing such distant objects requires cutting-edge technology and a bit of cosmic luck. Astronomers used the Hubble Space Telescope to capture its light, pushing the boundaries of what was thought possible. By analyzing the galaxy's redshift, a measure of how much its light has stretched as the universe expanded, they confirmed its record-breaking distance. But Hubble wasn't alone in this endeavor. Ground-based observatories and advanced computer models played crucial roles in interpreting the data and piecing together its story. The challenges of observing such distant galaxies are immense. Their light is faint, often obscured by intervening gas, dust, and the glare of closer objects. Yet the rewards are equally profound. GNZ 11 and its ilk provide a glimpse into the universe's earliest days, helping us understand the processes that shaped the cosmos. They also raise tantalizing questions about what came before. What secrets do even older galaxies hold? Could there be galaxies dating back to the first moments of the universe waiting to be discovered? Technological advancements are key to unlocking these mysteries. Instruments like the James Webb Space Telescope, with its unparalleled sensitivity to infrared light, are poised to peer even deeper into the cosmic past. By studying these ancient galaxies, we're not just exploring the origins of the universe, we're uncovering the story of how everything we know came to be. GNZ 11 is more than a scientific milestone. It's a reminder of the universe's boundless wonders and the endless potential for discovery. As we continue to probe the cosmos, each new finding brings us closer to understanding the forces that shape the universe and our place within it. And who knows, the next great discovery might be just over the horizon, waiting to rewrite our understanding of the cosmos once again. Galaxies are not isolated islands in the cosmos. They are dynamic systems, constantly evolving and interacting with their surroundings. One of the most dramatic ways they do this is through galactic winds, powerful outflows of gas and dust that can stretch across thousands of light years. These winds, driven by the explosive energy of supernova and the intense activity of supermassive black holes, play a crucial role in shaping the life cycle of galaxies. But how exactly do they work, and why are they so important? The story begins with the birth and death of stars. When massive stars reach the end of their lives, they explode as supernova, releasing enormous amounts of energy. These explosions can launch shock waves through the surrounding gas, propelling it outward at incredible speeds. Similarly, when supermassive black holes at the centers of galaxies feed on matter, they generate intense radiation and jets of particles that can push gas and dust out into space. Together, these forces create galactic winds that sweep through the galaxy, redistributing material and altering its structure. But galactic winds aren't just destructive, they're also a form of feedback, regulating the process of star formation. When gas is blown out of a galaxy, it becomes less available to form new stars, effectively putting the brakes on star formation. This feedback mechanism ensures that galaxies don't grow too quickly or burn through their fuel too soon. In fact, without galactic winds, galaxies might exhaust their gas reserves in a frenzy of star formation, leaving them barren and inactive. Observations and simulations have provided stunning insights into this dynamic process. For example, the galaxy M82, located about 12 million light-years away, is a classic example of a starburst galaxy with intense galactic winds. Its winds, driven by supernova, carry gas and dust far beyond the galaxy's disk, creating a glowing halo of material that's visible in X-ray and infrared light. Similarly, simulations have shown how supermassive black holes can launch winds that extend for tens of thousands of light-years, shaping the galaxy's evolution over billions of years. The implications of galactic winds extend far beyond individual galaxies. They're a key part of the larger cosmic ecosystem, transporting elements like carbon, oxygen, and iron from the interiors of stars into the vast intergalactic medium. These elements, essential for the formation of planets and life, enrich the universe and set the stage for future generations of stars and galaxies. Galactic winds are a reminder of the interconnected nature of the cosmos. They show how the smallest events, the death of a star or the feeding of a black hole, can have far-reaching consequences, shaping the evolution of entire galaxies and the universe itself. As we continue to study these powerful outflows, each discovery brings us closer to understanding the forces that drive the universe's grand narrative and our place within it. In the grand tapestry of the cosmos, it's often the smallest threads that hold the most significance. Enter dwarf galaxies, tiny, unassuming celestial systems that pack a cosmic punch far greater than their size suggests. These galaxies, often containing just a few billion stars compared to the hundreds of billions in galaxies like the Milky Way, are more than just cosmic afterthoughts. They are the building blocks of the universe, offering critical insights into how larger galaxies form and evolve. But why are these diminutive structures so important, and what secrets do they hold? The story of dwarf galaxies begins in the early universe, a time when the cosmos was a chaotic, swirling sea of gas and dark matter. Under the pull of gravity, small clumps of matter began to coalesce, forming the first galaxies, many of which were dwarf-sized. Over billions of years, these dwarf galaxies collided and merged, gradually growing into the massive galaxies we see today. In this sense, dwarf galaxies are like the primordial fossils of the universe, preserving clues about the conditions and processes that shaped the cosmos in its infancy. Despite their significance, studying dwarf galaxies is no easy task. Their small size and faintness make them difficult to observe, especially when they're located in the shadows of larger galaxies. Yet, advancements in technology, such as sensitive telescopes and powerful computer simulations, have allowed astronomers to peer deeper into their secrets. One surprising discovery is that many dwarf galaxies contain vast amounts of dark matter, far more than their visible stars would suggest. This has led scientists to rethink the role of dark matter in galactic formation and evolution, with some proposing that dwarf galaxies might be the best laboratories for studying this elusive substance. Another intriguing aspect of dwarf galaxies is their diversity. Some are isolated, drifting alone in the vastness of space, while others orbit larger galaxies like cosmic satellites. These satellite galaxies, such as the Magellanic Clouds near the Milky Way, often exhibit unique properties, including irregular shapes and active star formation. By studying these systems, astronomers can better understand the complex interactions between galaxies and how they influence each other's evolution. But perhaps the most compelling question is what dwarf galaxies can teach us about the universe's origins. Their simplicity and abundance make them ideal test subjects for theories about the early cosmos. For instance, the chemical composition of their stars and gas provides a snapshot of the universe's conditions billions of years ago, offering clues about how elements like hydrogen and helium transformed into the rich diversity of materials we see today. The study of dwarf galaxies is a reminder that even the smallest objects can hold the keys to unlocking the universe's greatest mysteries. They challenge us to look beyond the obvious, to explore the hidden corners of the cosmos, and to piece together the story of how everything we know came to be. As we continue to probe their secrets, each discovery brings us closer to understanding the universe's origins and our place within it. Picture the universe not as a random scattering of stars and galaxies, but as a vast, interconnected network, a cosmic web stretching across the fabric of space. This intricate structure, made up of filaments of gas and dark matter, connects galaxies like beads on a string, forming the largest and most complex framework we know. The cosmic web isn't just a stunning visual, it's the backbone of the universe, shaping how galaxies form, evolve, and interact over billions of years. At the heart of the cosmic web lies dark matter, the invisible glue that holds the universe together. Its gravitational pull draws ordinary matter, hydrogen, helium, and other elements into dense regions, forming the filaments that make up the web. Where these filaments intersect, galaxies and galaxy clusters emerge, creating nodes of light and activity. But the web isn't just a static map. It's a dynamic, ever-changing network, with gas flowing along its filaments to feed the growth of galaxies and fuel the birth of stars. Simulations have played a crucial role in uncovering the cosmic web structure. Using supercomputers, scientists have recreated the universe's evolution, starting from the Big Bang and tracing the formation of this vast network. These models reveal a stunning level of detail, showing how filaments of gas and dark matter weave together to form a tapestry that spans the cosmos. Observations have further confirmed the existence of the cosmic web, with telescopes detecting the faint glow of gas in these filaments and mapping their distribution across the universe. Cosmologists believe the cosmic web is central to understanding galaxy formation. Without it, galaxies wouldn't have the raw materials, gas and dust, needed to form stars and grow. The web also acts as a cosmic highway, transporting material between galaxies and influencing their evolution. For example, when filaments intersect, they can trigger bursts of star formation or even galactic collisions, reshaping entire regions of the universe. But the cosmic web isn't just a scientific curiosity. It's a window into the universe's deepest secrets, from the nature of dark matter to the origins of the first galaxies. By studying its structure and dynamics, astronomers hope to uncover clues about the universe's history and its ultimate fate. It's a reminder that the cosmos is more than just a collection of isolated objects. It's a vast, interconnected system, where every galaxy, star, and planet is linked by the threads of the cosmic web. As we continue to explore this intricate network, each discovery brings us closer to understanding the universe's grand design. The cosmic web is a testament to the beauty and complexity of the cosmos, a reminder that even in the vastness of space, everything is connected. And as we unravel its mysteries, we're not just learning about the universe, we're discovering our place within it. Among the most dazzling spectacles in the universe are starburst galaxies, cosmic powerhouses where star formation reaches breathtaking levels. These galaxies don't just produce stars, they do so at rates hundreds or even thousands of times faster than the Milky Way. Imagine a single galaxy birthing stars by the millions, lighting up the darkness of space with a brilliance that rivals entire clusters. But what drives such extreme activity, and what does it mean for the galaxy's future? The secret lies in the galaxy's environment. Starburst galaxies often arise in regions where immense clouds of gas and dust collide and compress under gravity. This process can be triggered by a variety of events, but one of the most common is galactic mergers. When two galaxies collide, their gravitational forces stir up the gas and dust, creating shock waves that ignite rapid star formation. It's a cosmic firestorm where the chaos of collision becomes the cradle of new stars. But mergers aren't the only catalysts. Intense radiation from a galaxy's central supermassive black hole can also drive star formation, as can interactions with nearby galaxies that funnel gas into the starburst region. These conditions create a perfect storm for star birth, with gas clouds collapsing under their own gravity and igniting into blazing hot stars. The impact of such intense star formation is profound. Starburst galaxies are often filled with massive, short-lived stars that burn brightly and die young, exploding as supernovae that enrich the galaxy with heavy elements. These explosions can trigger further waves of star formation, creating a cycle of birth and destruction that reshapes the galaxy over millions of years. Yet, this flurry of activity comes at a cost. Starburst galaxies burn through their gas reserves at an alarming rate, leaving them with little fuel for future star formation. Eventually, they may run out of gas entirely, transforming into quiet, aging galaxies with few new stars. The study of starburst galaxies offers a window into the dynamic processes that shape the universe. They remind us that even in the vastness of space, chaos can give rise to beauty, and destruction can pave the way for creation. From their origins in galactic collisions to their dazzling displays of cosmic fireworks, these galaxies are a testament to the universe's ability to surprise and inspire. While it's easy to focus on the visible wonders of galaxy stars, gas, and dust, there's an invisible force at work that's just as crucial: magnetic fields. These fields, though intangible, play a profound role in shaping the cosmos, from guiding the birth of stars to influencing the structure of entire galaxies. Yet, for decades, their importance was overlooked, hidden in the shadow of more tangible phenomena. Today, thanks to cutting-edge technology and innovative research, we're beginning to uncover just how vital magnetic fields are to the universe's grand design. Magnetic fields aren't confined to Earth or our solar system. They stretch across galaxies, weaving through the gas and dust that fill the interstellar medium. These fields act like cosmic conductors, channeling the flow of charged particles and shaping the paths of stars and gas clouds. During star formation, for example, magnetic fields can either help or hinder the process. On one hand, they can prevent gas clouds from collapsing under their own gravity, slowing star birth. On the other, they can channel material into dense regions, triggering the formation of new stars. It's a delicate balance, one that highlights the complexity of the universe's creative forces. But their influence doesn't stop there. Magnetic fields also play a key role in the dynamics of galaxies. They can stabilize galactic disks, helping to maintain the structure of spiral arms and prevent the galaxy from collapsing. They're also thought to drive the powerful jets of particles that shoot out from the centers of active galaxies, fueled by supermassive black holes. These jets, which can extend for thousands of light years, are shaped and directed by the magnetic fields that surround them. Studying these fields, however, is no easy task. Unlike stars or gas, they're invisible, leaving no direct trace for telescopes to detect. Instead, scientists rely on indirect methods, such as observing how they affect the polarization of light or the paths of cosmic rays. These techniques require precision instruments and complex models, making the study of galactic magnetic fields a challenging but rewarding frontier in astrophysics. What does this mean for our understanding of the universe? For one, it underscores the interconnected nature of cosmic processes. Magnetic fields are woven into the fabric of galaxies, influencing everything from the smallest star to the largest structure. They remind us that the universe is more than just the sum of its visible parts. It's a complex, dynamic system where forces we can't see play a critical role. As we continue to explore the mysteries of galactic magnetic fields, each discovery adds a new layer to our understanding of the cosmos. They challenge us to look beyond the obvious, to explore the unseen forces that shape the universe, and to appreciate the intricate web of interactions that make the cosmos a place of endless wonder. Stepping back in time to the universe's infancy, we encounter a cosmic landscape vastly different from the one we know today. Galaxies in the early universe, born just a few 100 million years after the Big Bang, were more than just relics of the past. They were the pioneers of cosmic evolution. These primordial galaxies, like GNZ 11 and EGC 8P7, offer a glimpse into a time when the universe was a chaotic, energetic place brimming with potential. But what sets these ancient galaxies apart from their modern counterparts, and what can they teach us about the universe's origins? One striking difference lies in their composition. Early galaxies were made almost entirely of hydrogen and helium, the simplest elements forged in the Big Bang. Heavier elements like carbon, oxygen, and iron, essential for planets and life, had yet to form, making these galaxies chemically pristine. Over billions of years, these elements would gradually accumulate through the life cycles of stars, enriching the universe and paving the way for the diverse galaxies we see today. The structure of these early galaxies also differs significantly. Unlike the well-defined spirals and ellipticals we're familiar with, they were often irregular and chaotic, with clumps of stars and gas forming haphazardly. This reflects the turbulent conditions of the early universe, where gravity was still pulling matter together into coherent structures. Yet, despite their chaotic beginnings, these galaxies laid the foundation for the cosmic order we see today. Recent observations have shed new light on these cosmic pioneers, thanks to technological advancements like the James Webb Space Telescope. With its unprecedented sensitivity to infrared light, Webb can peer back to the universe's earliest epochs, capturing the faint glimmers of these ancient galaxies. These observations have revealed that early galaxies were surprisingly bright and active, forming stars at rates much higher than expected. This challenges our understanding of how galaxies form and evolve, suggesting that the early universe was far more dynamic than we imagined. But perhaps the most profound question is how these first galaxies shaped the universe we see today. Their intense radiation and powerful stellar winds helped ionize the surrounding hydrogen gas, clearing the cosmic fog and allowing light to travel freely, a process known as reionization. This marked a turning point in cosmic history, transforming the universe from an opaque, featureless expanse into the transparent, star-filled cosmos we know. The study of early galaxies isn't just about understanding the past. It's about uncovering the forces that shape the universe's grand narrative. They remind us that even in its infancy, the universe was a place of creativity and transformation, where the seeds of galaxies, stars, and planets were sown. And as we continue to explore these ancient structures, each discovery brings us closer to understanding our cosmic origins and the story of everything we see around us. In the vast expanse of the universe, change is the only constant, and one of the most dramatic changes on the horizon, literally, is the collision between our Milky Way and its neighboring galaxy, Andromeda. This cosmic event, set to occur in about 4.5 billion years, will reshuffle the stars, gas, and invisible forces that make up our galactic home. But what exactly will happen when these two galaxies meet, and what does it mean for the future of our cosmic neighborhood? The Andromeda and Milky Way galaxies are currently hurtling toward each other at a staggering speed of about 110 kilometers per second. Despite the vast distance separating them, approximately 2.5 million light-years, gravity is inexorably drawing them together. When they finally collide, it won't be a head-on smash but a gradual, intricate dance that unfolds over billions of years. Simulations of this event paint a stunning picture. The galaxies will pass through each other multiple times, their gravitational forces pulling and twisting their structures until they merge into a single new galaxy. What's fascinating is that this merger won't be as destructive as it might sound. The vast distances between stars mean that direct collisions are unlikely. Instead, the galaxy's gas clouds will collide, triggering bursts of star formation and illuminating the cosmos with newborn stars. Over time, the chaotic swirl of stars and gas will settle into a more stable structure, likely forming an elliptical galaxy, a smooth, oval-shaped system vastly different from the spirals we see today. At the heart of this merger lies another intriguing element: the supermassive black holes of both galaxies. Found at the centers of the Milky Way and Andromeda, these black holes will eventually spiral toward each other, drawn by gravity. As they come closer, they'll release ripples in spacetime known as gravitational waves, a phenomenon predicted by Einstein and observed for the first time in 2015. When they finally merge, they'll create an even more massive black hole, anchoring the new galaxy's core. But what does this mean for Earth? While the collision will dramatically reshape the night sky, with stars from both galaxies mingling in a dazzling cosmic display, our solar system is unlikely to be directly affected. The chances of our planet being flung out into intergalactic space are slim, though its orbit around the new galaxy's center may shift. The Andromeda-Milky Way collision is more than just a distant cosmic event. It's a reminder of the universe's dynamic nature. It shows us that even the largest structures in the cosmos are subject to change, evolving through forces that span billions of years. And as we peer into the future of our galaxy, we're reminded that the universe is a place of endless transformation where even the stars we see today are part of a story far grander than we can imagine. Galactic archaeology might sound like a term straight out of science fiction, but it's a real and vital field of astronomy. Think of it as cosmic detective work, where scientists piece together the history and evolution of galaxies not by digging through soil but by studying stars. Each star is like a time capsule, preserving clues about its birth, environment, and the galaxy's turbulent past. The key to this detective work lies in a star's chemical composition and motion. When stars form, they inherit the elements present in the gas clouds around them. By analyzing the light from these stars, astronomers can determine their chemical makeup, revealing the conditions of the galaxy at the time they were born. For example, older stars tend to have fewer heavy elements, reflecting the early universe's simpler chemistry. Younger stars, on the other hand, are enriched with elements forged in the hearts of previous generations of stars, telling a story of cosmic recycling over billions of years. But it's not just about chemistry. The motion of stars also offers critical insights. Stars orbiting a galaxy carry imprints of its gravitational history, including past collisions and mergers. By mapping their movements, astronomers can reconstruct how galaxies grew and changed over time. It's like rewinding a cosmic film, watching as galaxies evolve from their chaotic beginnings to the structured systems we see today. So, how do astronomers gather this data? One of the most powerful tools is spectroscopy, which breaks down starlight into its component colors to reveal the chemical fingerprints of stars. Another technique involves precise measurements of stellar motion, often using space telescopes like Gaia, which has mapped the positions and velocities of over 1 billion stars in the Milky Way. Together, these tools create a detailed picture of a galaxy's history, uncovering stories that would otherwise remain hidden. One of the most surprising discoveries from galactic archaeology is the Milky Way's violent past. Studies have revealed that our galaxy has cannibalized smaller galaxies, absorbing their stars into its own structure. These remnants, known as stellar streams, trace the paths of ancient collisions, offering a glimpse into the Milky Way's formative years. As astronomer Amina Helmi puts it, the stars are our witnesses. They carry the memories of events that shaped the galaxy billions of years ago. Galactic archaeology is more than just a scientific endeavor. It's a journey into the universe's history. By studying the stars, we're uncovering the stories of galaxies, from their birth in the early universe to their growth through collisions and mergers. It's a reminder that the cosmos is not just a collection of objects, but a living, evolving system with a rich and complex past. And as we continue to explore these stellar time capsules, each discovery brings us closer to understanding the universe's grand narrative and our place within it. Hidden between galaxies, a vast and unseen reservoir of gas stretches across the cosmos, playing a critical role in the life cycle of galaxies. This intergalactic gas, though invisible to the naked eye, is a cornerstone of our universe's structure and evolution. Unlike the dense clouds within galaxies, this gas is diffuse and difficult to detect, making it one of the most challenging yet fascinating subjects in astronomy. So, what exactly is this gas, and why is it so important? Intergalactic gas is primarily composed of hydrogen and helium, the simplest and most abundant elements in the universe. It fills the voids between galaxies, forming a cosmic web that connects everything from tiny dwarf galaxies to massive clusters. This gas isn't just floating aimlessly, it's a vital resource for galaxies, feeding their growth and fueling the birth of stars. When galaxies pull this gas into their gravitational grasp, it can cool and condense, forming the building blocks of new stars and planets. Without intergalactic gas, galaxies would eventually run out of the raw materials needed to sustain their stellar populations. Observing this gas, however, is no simple task. Its diffuse nature makes it nearly invisible in most wavelengths of light. To detect it, astronomers rely on indirect methods, such as studying the absorption lines it creates in the light of distant quasars. These lines, like fingerprints, reveal the gas's composition and distribution, allowing scientists to map its presence across the universe. Advanced instruments like the Hubble Space Telescope and the upcoming James Webb Space Telescope are essential tools in this effort, offering unprecedented views of the cosmic web. The study of intergalactic gas has opened new doors to understanding the cosmic ecosystem. It reveals how galaxies are interconnected, sharing resources and influencing each other's evolution. For example, when galaxies collide or interact, the gas between them can be funneled into their centers, triggering bursts of star formation. This process not only shapes individual galaxies but also affects the larger structure of the universe, weaving together the threads of the cosmic web. So, how does intergalactic gas shape the universe? It's more than just a passive backdrop. It's an active player in the story of cosmic evolution. By feeding galaxies, fueling star formation, and connecting vast regions of space, it ensures the universe remains a dynamic and ever-changing place. As we continue to explore this hidden resource, each discovery brings us closer to understanding the intricate web of interactions that define the cosmos. As we explore the universe's vast array of galaxies, some stand out not for their size or brightness, but for their sheer strangeness. These are galaxies that defy the familiar classifications of spirals, ellipticals, and irregulars, cosmic oddities with shapes so unusual they seem almost otherworldly. From ring galaxies that resemble cosmic bullseyes to galaxies twisted into bizarre configurations, these structures challenge our understanding of galactic evolution and remind us that the universe is full of surprises. One of the most striking examples is Hoag's object, a galaxy that looks like a perfect ring of stars surrounding a glowing core. Discovered in 1950, This rare phenomenon is thought to have formed through a collision or gravitational interaction with another galaxy. The impact would have sent ripples through the gas and dust, triggering the formation of stars in a circular pattern. It's a stunning example of how violent events can give rise to unexpected beauty. Another fascinating case is the Tadpole Galaxy, whose long tail of stars and gas stretches across hundreds of thousands of light-years. This peculiar shape is the result of a smaller galaxy being pulled apart by the tadpole's gravitational forces, leaving behind a trail of debris that resembles a cosmic tadpole. Such interactions are a testament to the dynamic and often chaotic nature of the universe, where galaxies are constantly reshaping each other through their gravitational dance. But not all unusual shapes are the result of collisions. Some galaxies, like NGC 474, have shells or layered structures that give them a unique appearance. These features are thought to be remnants of past mergers, where the absorbed galaxy stars were scattered into distinct patterns. Over time, these patterns settle into shells, creating a layered effect that's as mesmerizing as it is mysterious. The study of these unusual galaxies isn't just about cataloging their forms, it's about understanding the forces that shape them. Whether it's the gravitational pull of a neighboring galaxy, the shockwaves of a collision, or the remnants of an ancient merger, each galaxy tells a story of transformation and resilience. These cosmic oddities also highlight the diversity of the universe, reminding us that there's no single blueprint for galactic evolution. From ringed wonders to tadpole tails, they showcase the creativity of the cosmos, where even the most bizarre shapes have a place in the grand design. As we continue to explore these unusual galaxies, each discovery adds a new piece to the puzzle of how the universe works. They challenge us to think outside the box, to embrace the unexpected, and to marvel at the endless variety of the cosmos. And in doing so, they remind us that the universe is a place of infinite possibilities, where even the strangest shapes can reveal profound truths about the nature of existence. Beyond the visible light of stars and galaxies, there's an invisible force coursing through the cosmos' cosmic rays. These high-energy particles, traveling at nearly the speed of light, originate from some of the most violent events in the universe, like supernova explosions and the jets of active galactic nuclei. But cosmic rays aren't just cosmic relics. They're active participants in the life of galaxies, influencing everything from star formation to the structure of the interstellar medium. So, how do these unseen particles shape the evolution of galaxies? Let's start with their origins. Cosmic rays are born in extreme environments, where immense energy accelerates particles to incredible speeds. When a massive star explodes as a supernova, for example, the shockwaves can propel protons and other particles into space, creating a flood of cosmic rays that permeate the galaxy. Similarly, the intense magnetic fields around supermassive black holes can launch particles across vast distances, sending cosmic rays into the wider universe. Once released, these particles become a driving force in galactic processes. When cosmic rays interact with the gas and dust of the interstellar medium, they can trigger chemical reactions, ionizing atoms and molecules. This ionization not only affects the temperature and pressure of the gas, but also plays a crucial role in star formation. By heating the gas, cosmic rays can prevent it from collapsing into new stars, effectively slowing down the rate of star birth in certain regions. But their influence doesn't stop there. Cosmic rays also contribute to the dynamic environment of galaxies. As they travel through space, they generate magnetic fields, adding to the complex web of forces that shape galactic structures. These fields can stabilize gas clouds, helping to maintain the spiral arms of galaxies like the Milky Way. At the same time, cosmic rays can drive powerful outflows of gas, redistributing material across the galaxy and influencing its evolution over billions of years. The study of cosmic rays has opened new doors to understanding the universe. By observing their effects on distant galaxies, astrophysicists have gained insights into the processes that govern galactic evolution. As Dr. Elena Amato, an expert in cosmic ray astrophysics, explains, cosmic rays are like the unsung heroes of the cosmos. They may be invisible, but their impact is profound, shaping the life cycle of galaxies in ways we're only beginning to understand. So, what does this mean for our understanding of the universe? Cosmic rays are a reminder that even the smallest particles can have a massive impact. They connect the smallest scales of particle physics to the largest structures in the cosmos, weaving together the story of how galaxies form, evolve, and interact. As we continue to explore the universe, each discovery about cosmic rays adds a new dimension to our understanding. They challenge us to look beyond the visible, to explore the hidden forces that shape the cosmos, and to appreciate the intricate web of interactions that make the universe a place of endless wonder and discovery. When we think of life beyond Earth, our minds often drift to distant planets within our own galaxy. But what if life exists in galaxies far beyond the Milky Way? The search for habitable galaxies is a bold and ambitious endeavor, one that challenges us to expand our horizons and rethink the possibilities of life in the cosmos. Not all galaxies are created equal when it comes to fostering life. The types of stars they host play a crucial role. Galaxies rich in stable, long-lived stars like our Sun may offer better environments for life to develop. These stars provide a steady source of energy over billions of years, giving planets the time and stability needed for life to evolve. On the other hand, galaxies dominated by massive, short-lived stars could be less hospitable, as their intense radiation and explosive deaths might sterilize nearby systems. The galactic environment also matters. Galaxies with fewer cosmic hazards, such as intense radiation from active galactic nuclei or frequent supernova, are more likely to support life. Similarly, the presence of essential elements like carbon, oxygen, and nitrogen, building blocks for life as we know it, is a key factor. These elements are forged in the hearts of stars and dispersed through supernova, enriching the galaxy's interstellar medium and providing the raw materials for planets and potentially life. Astrobiologists are leading the charge in this search, using tools like the James Webb Space Telescope to study distant galaxies for signs of habitability. By analyzing their chemical composition, star formation rates, and environmental conditions, they are identifying regions that could harbor life, as Dr. Sarah Rugheimer, an astrobiologist at the University of Oxford, explains, the search for life isn't just about finding Earth-like planets. It's about understanding the broader conditions that make life possible across the universe. This raises a profound question. Are we alone in the universe, or is life more common than we think? The discovery of even a single habitable galaxy could revolutionize our understanding of life's potential. It would suggest that the universe is a place teeming with possibilities, where life could arise in countless forms and environments. The search for habitable galaxies is more than a scientific quest, it's a journey of curiosity and imagination. It challenges us to look beyond our own cosmic backyard and consider the vast, interconnected nature of the universe. As we continue to explore, each discovery brings us closer to answering one of humanity's oldest questions. Are we truly alone, or is life a universal phenomenon, waiting to be discovered in the farthest reaches of the cosmos? As we peer into the cosmos today, it's impossible not to wonder what tomorrow might bring. The future of galactic exploration is brighter than ever, thanks to a wave of groundbreaking technologies and missions designed to push the boundaries of what we know. From next-generation telescopes to ambitious space missions, the tools at our disposal are poised to unlock secrets of distant galaxies that have remained hidden for billions of years. At the forefront of this revolution is the James Webb Space Telescope, a marvel of engineering already transforming our understanding of the universe. Unlike its predecessor Hubble, Webb specializes in infrared light, allowing it to peer through cosmic dust and observe the earliest galaxies with unprecedented clarity. Its discoveries are shedding light on how galaxies formed and evolved in the universe's infancy, offering a glimpse into a time when the cosmos was still taking shape. But Webb is just the beginning. The Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will map the universe in incredible detail, capturing images of billions of galaxies in a single sweep. This wide-field approach will help astronomers study the large-scale structure of the universe, tracing the distribution of dark matter and uncovering the forces that drive galactic evolution. Meanwhile, ground-based observatories like the extremely large telescope ELT in Chile will complement these efforts with their massive mirrors, capturing sharper images of distant galaxies than ever before. Space missions are also set to redefine galactic exploration. Projects like the European Space Agency's Euclid and NASA Spherex will map the universe in 3 dimensions, studying the cosmic web and the distribution of galaxies across vast distances. These missions aim to answer fundamental questions about the nature of dark energy and how it influences the universe's expansion, providing clues about the ultimate fate of galaxies. The excitement among astronomers is palpable, as Dr. Priya Natarajan, an astrophysicist at Yale University, puts it, "We're on the cusp of a new era in cosmology." The tools we have today are unlocking mysteries that were once thought to be beyond our reach. With each new mission and technological advancement, the boundaries of our knowledge are expanding, offering fresh perspectives on the cosmos. So, what mysteries might we uncover in the next decade? Could we find evidence of life supporting planets in distant galaxies? Will we unravel the secrets of dark matter and dark energy, the invisible forces shaping the universe? Or will we discover entirely new phenomena that challenge our understanding of reality? The possibilities are as vast as the cosmos itself. The future of galactic exploration isn't just about answering questions, it's about sparking new ones. It's a journey of curiosity and discovery, where every observation, every mission, and every breakthrough brings us closer to understanding the universe's grand narrative. And as we embark on this adventure, one thing is certain: the cosmos still has countless stories to tell, waiting for us to